Welcome, everyone. Air travel is one of the most complex and coordinated systems in the world. Each day, tens of thousands of aircraft move through controlled airspace with tight schedules, dynamic weather, and strict safety protocols. Air traffic control today is built on radar tracking, voice communication, and human judgment. Controllers monitor aircraft using radar screens and satellite data, issuing real-time instructions over radio. These controllers coordinate takeoffs, landings, altitude changes, flight paths, and reroutes due to weather or congestion. While systems like ADS-B and digital data links have improved situational awareness, the process remains largely manual. Human controllers handle everything from workload prioritization to conflict resolution. The job is demanding. Controllers work in high-stress environments with little margin for error. Human fatigue, distraction, and communication breakdowns can lead to incidents. As global air traffic grows, the demand for air traffic controllers increases, but training new personnel takes years. In some regions, controller shortages are already causing flight delays. These challenges have sparked interest in AI-based decision support and automation to improve efficiency, reduce risk, and scale the system. Artificial intelligence is entering the picture in several ways. One of the most promising is AI-assisted air traffic management. Systems are being trained to predict potential flight conflicts, reroute traffic around congestion, and recommend optimal departure or landing sequences. Unlike human controllers who can focus on only a few aircraft at once, AI can analyze hundreds of flights simultaneously, identifying patterns and resolving problems proactively. NASA has developed a system called ATD-2, which uses machine learning to optimize the timing of departures at busy airports. The system reduces delays by coordinating takeoff sequences between airport surface traffic and en route airspace. In trials at Charlotte Douglas International Airport, ATD-2 demonstrated significant reductions in fuel burn and taxi time. It is now being integrated into the Federal Aviation Administration's broader modernization program. Another example is Eurocontrol's AI-powered integrated network management system in Europe, which uses predictive analytics to assess congestion and issue rerouting suggestions hours before problems occur. These systems act as advanced assistants, helping human controllers make better decisions faster. Over time, they could take on more direct responsibilities, especially in lower risk or lower traffic airspace. In parallel, AI is also being developed for use in aircraft themselves. The concept of pilotless flight is not new, but recent advancements are pushing the idea from theory toward reality. Modern commercial aircraft are already heavily automated. Autopilot systems can handle most of a flight's duration. Pilots typically take over during takeoff, landing, and emergencies. However, these systems follow rigid logic and require human input for unexpected situations. Next-generation AI systems are being designed to interpret complex scenarios, respond to novel conditions, and make autonomous decisions. Ground-based pilots can monitor the flights remotely and take control if needed. These systems are being tested with small turboprop aircraft and may expand to larger cargo planes before entering passenger service. One of the main advantages of AI pilots is consistency. Unlike humans, AI does not get tired, distracted, or emotionally compromised. It follows instructions precisely and can process vast amounts of data instantly. In emergencies, AI may respond faster and more rationally than a human. In complex environments like bad weather, heavy congestion, or equipment failure, AI systems could enhance safety by continuously calculating the best course of action based on live inputs. On the ground, airport control towers are also being reimagined with AI. The traditional tower, staffed by controllers watching aircraft through windows and screens, is being replaced in some locations by remote digital towers. These towers use high-resolution cameras, microphones, radar feeds, and artificial intelligence to monitor airport operations from a centralized facility. AI can track aircraft, detect potential runway incursions, identify wildlife or foreign objects, and suggest optimal gate assignments. For example, London City Airport has implemented a remote digital tower operated from over 80 miles away. AI helps controllers interpret visual and sensor data, enhancing situational awareness and enabling tighter coordination. As airports grow more complex and face staffing pressures, these smart towers offer a scalable solution that combines automation with human oversight. Despite these advancements, full autonomy is not yet a reality. and may not be for some time. The aviation industry is extremely risk-averse by design. Any system that replaces human judgment must meet high standards for reliability, explainability, and accountability. Regulators must be able to certify not only that the AI works, but that it will work safely in rare and unforeseen situations. Additionally, public trust in AI-piloted planes remains low. Surveys show that most passengers are currently uncomfortable with the idea of flying without a human pilot on board. This resistance may fade over time, especially as AI handles more behind-the-scenes tasks successfully. But for now, manufacturers are focusing on hybrid models, one pilot with AI assistance, or remote supervision of autonomous cargo flights before transitioning to passenger use. Legal and ethical questions also arise. If an AI-controlled plane crashes, who is liable? The manufacturer, the airline, the software developer? These issues are not yet resolved. Insurance models, regulatory frameworks, and international aviation law will all need updates before full autonomy can be widely adopted. In the meantime, the most likely path forward is a gradual evolution. Human controllers and pilots will remain central for the foreseeable future, but they will increasingly be supported by AI tools that enhance their situational awareness and reduce workload. These tools will help detect risks earlier, optimize traffic flow, and make complex decisions under pressure. AI copilots could become standard in the cockpit, advising human pilots, monitoring systems, and taking over repetitive or high-load tasks. In air traffic control centers, AI assistants might handle routine spacing and sequencing tasks, freeing human controllers to focus on exceptions and strategic decisions. Over time, these systems could assume greater autonomy in low-risk situations, such as managing unmanned cargo corridors or regional airports during off-peak hours. By 2032, it is plausible that some regional cargo aircraft will fly without human pilots guided by AI and monitored remotely. Smart towers may become the norm at smaller airports, with AI managing routine operations while alerting human staff only when needed. In major metropolitan areas, hybrid human-AI systems could manage complex traffic patterns, reducing delays and increasing throughput without compromising safety. The integration of artificial intelligence into aviation is not about removing humans entirely, at least not yet. It is about enabling better decisions, faster responses, and safer skies. As air traffic continues to grow and global mobility expands, the need for smarter, more scalable control systems becomes urgent. AI offers a path to meet that challenge, one intelligent decision at a time. Thank you very much for watching. Please like and subscribe.